All right, welcome back. So, what we're looking at now is going to be a little bit about how the actual control of this cardiac cycle is taking place. So, we're going to be looking at what is referred to as the cardiac conduction system. So, what these are specialized non contractile cardiac myocytes. So, these are cardiac muscle cells that don't have the actual contractile mechanisms in them. But what they are capable of doing is transmitting action potentials down along them, and it's going to be able to actually control this throughout the heart. So, what we're going to see here is this is going to start with what is referred to as the sinoatrial node and move through the atria. It then is able to connect to what is referred to as the AV node, and that is going to then link this to the ventricles. And what we're going to do is spend a little bit of time talking about how this works. So what is going on here is we have these, and this is up in kind of near the right atrium. We have this area called the sinoatrial node. What is going to happen here is these are kind of self-contractile, well, not self-contractile, but self-pulse forming cells or signal forming cells. How this works is there's actually, and again, we'll see how much I make you go into depth on this one, but what you have going on here is you have these sodium leak channels that are going on in this cell. So what's going on here is you have these sodium leak channels that are allowing sodium to go into the cell. What's going to happen, again, we pump this out, there's sodium that's leaking in. To me, I always kind of say it's a lot like if you've ever been to a water park, one of those dump buckets, you have water going into the bucket at a certain rate. Sooner or later, that bucket reaches a threshold where it dumps over. This is what's kind of going on with the SA node. You have this sodium ion leak channels that are going in here, and what's going to happen is sooner or later it reaches a threshold that is going to open up fast and slow calcium channels, which are actually going to allow this overall cell to depolarize and generate an action potential, which is going to travel over the entire atria. And we're going to see that our body can influence this with the sympathetic or the parasympathetic channels and either cause that leak to happen faster or slow down that leak. But the SA node, again, has this leak channel going on here. If we get a sufficient level of sodium leaking here, it's going to reach this threshold that causes that depolarization and repolarization as the potassium goes back in here. And again, opens up calcium channels. And this is how we're going to actually fire off this node. So what happens is once this happens, you're going to distribute, because this is in that cardiac muscle of the atria, and we said all these muscle cells are connected. This is going to move from one muscle cell to another, and it's going to travel over that entire atria and have it depolarize all together through these gap junctions. And this means that as they reach that point in their little depolarization and contraction, means all these cells are also going to contract together at the same time. So you have this conduction through the atria, this contraction of the atria all together. One of the things this is working to is what is referred to as the AV node. So near the tricuspid valve, you have this AV node. This AV node has these cells that are much smaller diameter, fewer gap junctions, and these are actually going to slow down this depolarization for a period of time. And this AV node and the connecting cells that are with this is the only connection through that fibrous skeleton. So remember we said that the atria and the ventricles are fully isolated electrically, at least the muscle cells. This is the only connection between these two. So this is what is going to allow that depolarization to move from the atria down to the ventricles through this fibrous skeleton. But this delay and the slowdown in here is actually allowing the mechanical contraction of the atria to finish before we get the depolarization and contraction of the ventricles. So we need to slow it down a little bit so we mechanically have enough time to finish contracting the atria before we get a contraction of the ventricles. What we don't want is basically like people trying to get in and out of the same door where you have people pushing on both sides of the door and no one's going through. So that's why we have this delay there. So that's this atria finish contracting, forcing the blood in the ventricles before the ventricles start their contraction. So that AV delay, again, letting this mechanically happen. AV node near the AV valve of the right side of the heart, near that tricuspid valve. So again, let's finish off that contraction and emptying of the atria before the ventricles start the contraction. And again, this should be the only route that connects that atrial depolarization to the ventricles. Again, the only thing that should be going through that fibrous skeleton unless we're having some type of pacemaker put in. So what we're then going to see is once that action potential gets through that delay at the AV node, it is going to move through what is called the AV bundle or the bundle of His. To the left and right, what are called the bundle branches, and then move up each side of the ventricles to these Purkinje fibers. And this is going to happen actually quite quick, especially when it gets to these Purkinje fibers. This is a very fast depolarization that travels through these and is going to really allow it to get to a lot of these ventricular muscle cells all at once. So we're going to get this ventricular muscle functioning all together at once to trigger a contraction. And again, this is kind of, sorry. Accidentally bumped it. This is what's occurring right here. You have this bundle of His or the AV bundle. And then I'm going to go in the left and right bundle branches. And then you can see these are the Purkinje fibers going up into that muscle. So it travels down around here, down to the tip, and then all the way up through those Purkinje fibers really quickly. And then we're going to see this whole ventricular muscle, because of these gap junctions, gets stimulated all together. And we're going to get the depolarization that travels there, and we're going to get this functioning all together to lead to a depolarization followed by a contraction of all this ventricular muscle. Again, the Purkinje fibers are large in diameter, so that means they can move there really quickly. Papillary muscles also have Purkinje fibers going up to them that are there to cause them to contract immediately, which are going to help keep those valves closed. And we're going to start getting this depolarization contraction occurring at the apex and working its way superior up the heart to really efficiently move that blood out through the aortic and pulmonary valves. And again, this kind of takes you through this. Again, action potential generated at SA node. Again, it's these sodium leak channels, like water going into a dump bucket that as soon as it reaches the threshold, opens up calcium channels, lets all this flood in, leads to that depolarization, and then repolarization by potassium channels there. But that is going to cause an action potential to travel out through the atria over to the AV node, where we have a delay in the AV node because of the smaller diameter and fewer gap junctions, which is allowing the atria to finish their contraction. It is then going to move down the bundle of His through the bundle branches up to the Purkinje fibers, and we're going to get depolarization and contraction starting at the apex of the heart and working its way superiorly up the ventricles as a unit to cause the ventricles to contract and eject that blood out of the heart. So again, the atria work as a syncytium, the ventricles work as a syncytium as a single unit. And in general, this impulse should happen about 60 to 80 to 100 times a minute as the normal heart rate. So the SA node should depolarize about 60 to 100 times a minute. Each one of those should trigger one cardiac cycle, one set of the heartbeat through there. And again, it is a repeating thing here. Again, that SA node, again, acting a lot like a dump bucket, water flowing into it, or sodium flowing into it. When it reaches the threshold, it's going to dump that, which is dumping a bunch of calcium in there, leads to that depolarization, and then buckets reset by potassium ions and starts having that leak happen again. How it kind of works with the sympathetic and parasympathetic, in all honesty, is the sympathetic, it's like turning the water up. So what you do is you increase the leak rate on those sodium channels when you are getting sympathetic stimulation to the heart, which means it's going to get to that threshold and dump quicker each time if you have more water going into the dump bucket. Parasympathetic, it actually increases the flow of potassium back into this cell, which means you're kind of filling it with the sodium bucket, but you also have a little hole in the bottom, which is going to take longer for that bucket to fill each time and will actually slow down the rate of these impulses. It also influences the AV node to increase the delay at the AV node with that parasympathetic. Again, very dependent upon oxygen and good blood supply. These do not fatigue. We're going to see that cardiac myocytes compared to skeletal muscle cells also have a very long refractory period, so they can't self-stimulate and get a continuing contraction moving around in there. And again, that long refractory period keeps, there is a mechanical speed limit to the heart as well. So, I mean, this longer refractory period means that there's always enough time for the blood to go in there and fill. If the heart was beating too fast, you're not going to mechanically have enough time for that blood to move in, move from the atria to the ventricle, move out of the heart before it was contracted again. So there really is kind of this speed limit of around, right around 200 beats a minute, a little bit over. The heart can get every once in a while, but you're not going to see heart rates of 300-400 beats a minute. It's low 200s is generally the fastest heart rate you usually will see. Most people, you don't even see that high. Most normal heart rates are in the max heart rates are in the 190s to approaching 200. You generally won't see much above that. The other thing this does is it helps prevent any retrograde excitation, where by having this long refractory period, you can't have one part of this cardiac muscle stimulating and getting this kind of rotating back and forth type of excitation that isn't being triggered by the AV node, so it can't feed back up itself. What we're going to see is the SE node should be the normal pacemaker of the heart. So generally the conduction system should be fired off every about 60 to 100 beats a minute by this SA node. Again, those leak channels triggering that to happen. What we're going to see is the AV node can act as a default pacemaker if for some reason the SA node stops working. The main thing with this one though is the AV node, the leak channels in here are a little bit slower. So what this means, if there was no SA node activity, the AV node would actually be getting enough leak by the sodium channels to trigger a depolarization about 40 to 50 times a minute. This is fast enough to sustain life, not particularly efficient. And the other thing is you're not getting any atrial depolarization with this one, so you're not getting any atrial contraction. But 40 to 50 beats by the AV node leading to ventricular contraction 40 to 50 times a minute is enough output for the heart to maintain life. This would be about 70% of the normal amount of blood getting into the ventricles if the AV node is only firing by that passive filling, but it is enough to sustain life. Again, because the SA node generally fires off sooner, you are going to depolarize that AV node sooner, and that's where you get the 6100. If both the SA node and the AV node were impaired, the ventricular myocytes themselves will try to beat. The leak channels in these ones are going to be about 20 to 40 beats a minute, which really will not sustain life, but it will attempt to take over. So these are, that primary would be the SA node, secondary and tertiary pacemakers of the heart are that AV node, and those ventricular cardiac myocytes respectively are the primary, secondary, and tertiary pacemakers of the heart. And again, anything but the AV node, anything but the SA node we refer to as an ectopic pacemaker. What can also happen is sometimes you can get abnormal contractions happening in the heart. So flutter is this idea of it's still functioning as a unit, but it's happening really quickly. So atrial flutter would be attempting to contract 200 to 400 times a minute. It can become atrial fibrillation. Fibrillation is, atrial flutter means the whole thing is trying to contract 200 to 400 times a minute. Atrial fibrillation means each part of that atria is kind of doing its own conversation. And I always use the example of fibrillation as kind of like when we're doing normal classes. When the instructor walked in at the beginning of the class, everybody's having their own little conversation, everybody's doing their own thing. That is this idea of fibrillation. Each little part of the heart is having its own little conversation. Again, both atrial flutter and atrial fibrillation are generally not life-threatening. They can be not good. They can lead to increased chances of stroke, but they're generally not life-threatening because the heart still, if you have the ventricles acting normally, is still doing about 70% of its normal output. PVCs are premature ventricular contractions. Sometimes stimulants or stress can lead to an abnormal kick of this AV node where it fires off when it shouldn't be and is actually contracting out of sequence. unless these start happening a ton, generally not life-threatening, not detrimental unless it happens a ton. What is very, very life-threatening is ventricular fibrillation. Again, if the ventricles don't contract, no blood is leaving the heart. So no blood going to the systemic circuit, no blood going to the lungs. If the ventricles aren't contracting coordinated fashion, that will be a life-threatening thing. VFib or ventricular fibrillation is each part of the ventricle kind of doing its own thing. This is when you would actually get a defibrillator. So a defibrillator is when you're shocking the heart. Some interesting stuff with all this one. So if you've ever watched TV and watched any medical show, they will show, here's a person, that flat line. They go clear, zap you. Just want to let you know, that is a rhythm you would never actually shock. So asystole is no electrical activity in the heart. I always kind of use the example of people are all talking at the beginning of the class and all of a sudden I took my hands, and I usually do this in person. I'm not going to do this on my computer table because I don't want to break it. But what I would do is like, okay, everybody talk to yourself, and then boom, you slam the table. All of a sudden, all the people that are having a conversation turn and look at you. That is basically what a defibrillation does. Each little part of the heart is having its own little electrical conversation. You go boom with these electrical things. What you're doing is you're depolarizing the entire heart. It all goes contract, relax. What you're then hoping takes place is the SA node steps in and starts doing that coordinated fashion again. That is what a defibrillator does. If you're having asystole, that means there is no contraction, no electrical activity in the heart. Hitting that with a paddle, you're clearing. If you have no electrical activity, there's nothing to clear. No abnormal conversation to clear. No abnormal contraction to clear. VFib is something you would actually shock. This is each part of the heart doing its own thing. You go clear, you get the whole thing to electrically contract, relax, and then you hope that SA node takes over. Asystole, you don't shock that because all you're clearing the electrical activity of a heart that has no electrical activity. What you should be doing on that one is you should be pushing epinephrine or norepinephrine. That is going to stimulate that SA node to fire off quicker. Chest compressions, sometimes a precordial thump where you hit them in the chest can kickstart the heart in that case. But shocking it is not something that is going to help with a flat line. That being said, it's been in the movies since probably Flatliners, the Julia Roberts, Kiefer Sutherland, one of the Baldwins type of thing. Kevin Bacon, big surprise on that one. That's that movie. It's been there since that. And again, almost every medical show you'll see a flat line, they'll say clear and they'll shock the person. It is a rhythm you would honestly in real life never shock. Never actually hit it with a defibrillator. But it's something you see over and over again. So sorry to ruin movies and TV shows for you, but you'd never shock a flat line. Again, what is happening within this muscle? You're going to get this depolarization, which is that action potential that goes through there, opening these sodium gates, which leads to calcium coming in here and leads to a contraction of this. So in the case of the heart, it's a lot more extracellular calcium getting into the heart than it is. There is some in the sarcoplasmic reticulum as well, but more from the outside of the heart getting in there and leads to the actual contraction happening. But we get depolarization of this cardiac muscle due to those changes in the voltage-gated sodium channels. We then get calcium flooding in here into the cells, stimulates the sarcoplasmic reticulum to release more. This is that plateau phase in cardiac muscle. This is what's going to lead to the contraction taking place. You are then going to get repolarization by the closing of the sodium and calcium gates and potassium gates remaining open, which is going to reset this cardiac muscle to its resting state. So if you were to look at a voltmeter of cardiac muscle, you would see something that looks like this. The depolarization due to the sodium and the calcium being open, but at this point all those close and you get repolarization due to those potassium channels getting you back to that resting membrane potential. Same thing is happening at the SA node somewhat, but again, this should be happening 60 to 100 times a minute under normal conditions at that SA node. The entry of that calcium in there is going to start those events that are going to lead to the actin and myosin interaction, removing the troponin and tropomyosin, blocking this. We pump this calcium back out, so as reuptake into the sarcoplasmic reticulum, removal from here, much like we saw before on skeletal muscle, removes that from that troponin and inhibits that, and they go back to that resting state. So it is this calcium flooding in, lets the actin and myosin interact. We then remove it really quickly, lets it go back to its resting state. We then, with each cardiac cycle, we're getting that calcium in, back out, over and over again. Again, with skeletal and cardiac muscle, we both have a refractory period. What we see with cardiac muscle is there's going to be a much longer refractory period. Skeletal muscle is much shorter. There is going to be this depolarization, repolarization, this contraction, relaxation cycle with a lag time between when you actually trigger the action potential and you get the contraction. What we end up seeing with cardiac muscle is the refractory period is way longer. We have this extended plateau phase. It's about 100 times longer of this kind of refractory period relative to skeletal muscle. What this means is, unlike with skeletal muscle where we talked about tetanus, you cannot get a tetanus response in cardiac muscle. It is not capable of going to a sustained contraction. What this means is the heart is always going to get contracted, goes back to relaxed state where it can try to then get stimulated again to contract and continue this pumping mechanism. It can never get into a locked contraction phase. And again, you can kind of see the difference right here, the depolarization, repolarization that happens in skeletal muscle and how quick the reaction and relaxation of skeletal muscle is, where if we look at cardiac muscle, there's that longer plateau phase, which leads to a much longer depolarization phase, and in all honesty, a quicker, not as nearly as quick contraction and going back to relaxation. So again, we're going to see it is very similar, but skeletal muscle is a much faster depolarize, repolarize, contract back into relaxation than we see with cardiac muscle. And if you were to look at different action potentials in different areas of the heart, you can kind of see each of these is a little bit different depending on the area that you're looking at. When we get into EKGs or ECGs, depending on which way you want to use the letters, they both mean the same thing. You can actually look at each of these areas here, but you can see longer plateau on the ventricle versus the atrium. You can see the SA node is this depolarization, repolarization, and that's going to happen over and over and over again. So what we're going to start looking at next is going to be a little bit of these EKGs and how we can actually register what is going on electrically in the heart. Again, understanding how what we talked about on this one, how that depolarization through the cardiac conduction system leads to the cardiac cycle is kind of a key idea. So make sure you understand how what we've talked about on this one relates back to what we talked about with ventricular and atrial systole and diastole, and how that sequence of events in the cardiac cycle is actually being controlled by the cardiac conduction system that we've walked through on this one. So that is it for this one right now. I will see you next time.